So we're going to get into some exam questions. I picked out a few of the ones that are in the booklet here. I'm not going to do them all because we'd be here all night. But we'll pick out a few ones to kind of look at that should cover a lot of the different aspects that we have for hypothesis testing. So we've kind of already considered that there's kind of the three different ways of doing the tests, depending on as well which parameter we're actually testing. So if we're testing proportion, for example, there really is, I suppose, really only one way. And if we're doing the mean, then we have the three different ways, bearing in mind that they could request a particular one. So looking at this question, this is from last year's for population proportion. Peak Hotel was rated the best hotel chain in Europe by 75%. So reference of a percentage, that's a proportion. So straight away I'm like, stunning, it's a proportion. They carried out a survey of a sample of 1,000 customers to see if the percentage had changed. 765 rated that the best hotel chain carry out a hypothesis test. So let's see what we know. We know P hat, which is the proportion of the sample, so 765 of the 1,000 in the sample, which is 0.765. We know the sample size n is 1,000. Anything else that I need here? No. Okay, so let's lay out our hypotheses first of all. So first step is always just hypotheses. So my hypothesis here is that the proportion has not changed and is still 75. So 0.75, remembering that we usually use this in terms of decimals. The null hypothesis then would be that it has changed and is no longer 0.75. My test then, because it's proportion, is going to be a confidence interval. So a confidence interval for population proportion is p hat plus the error and p hat minus error. Because I have, I suppose, enough information here, we're going to use the more accurate of the two errors, which is the standard error, making sure we multiply that by 1.96 to account for, I suppose, the level of confidence here that we want, basically the standard deviations or the standard error that we're allowing for here. So let's fill in what we can here, bearing in mind as well, we're going to use p hat as an estimator for p in calculating our standard error here. Okay, even though yes, we do have a value that we're testing for p, since we're only testing it and it's not the exact value, then we don't use it in our calculation of the error. So 1 minus 0.765 all over the sample size, which is 1,000. And the same on the other side. I'll give myself a bit of extra space here as well. So 0.765 minus 1.96 square root of 0.765, 1 minus 0.765 all over 1,000. So laying out my confidence interval here, I'm just going to calculate this value, plus 1.96 times the square root of 0.765, 1 minus 0.765, all over 1,000, which is 0.79. 1 there. It's not seeming right for me yet. That seems okay. Okay, and going on the other side, then we'll subtract that value also and get 0.73. 738 or 739. So we'll go 7387 and 791. Let me see. 7913. Okay, we'll go to four decimal places there. Okay, so that's our hypothesis test. Our third step was always our decision. So we look at the claim here, which is 0.765. So as 0.765 falls within the null hypothesis, we fail to reject. Okay, so fail to reject here. So we fail to reject. And then looking at the fourth step here, which is our kind of conclusion, okay, and that obviously includes our decision here as well. So just kind of continuing ourselves on a little bit and tying this back to the question. So based on the test, or the hypothesis test, at 5% level of significance, there is insufficient evidence to suggest the mean, or let's tie it back to the question, there is insufficient evidence to suggest the proportion of customers rating PK Hotels the best chain has changed from 75%. So we're basically saying here, because we've failed to reject, that means there's not enough evidence here for us to say that it has changed. So we can't say with certainty that it has changed. Doesn't mean it hasn't, but we can't say that it has. Okay, let's keep moving. I'm just going to kind of fly through these. So second question here. In Ireland, players' scores in an online word game are approximately normally distributed, we like to see, with a mean of 3.87. So immediately I'm taking note of that, thinking, right, it's mean, it's average here. Standard deviation of 0.36. A random sample of 64 Galway players has a mean score of 3.74. Based on this, a local newspaper claims that Galway players have a different mean score to players in Ireland. Use this information to construct a confidence interval for the mean score of all Galway players. So let's have a look at that. X bar is sample mean here, which is 3.74. Standard deviation is 0.36. Confidence interval is mu is X bar plus 1.96 times sigma over root n. So using the standard error here and subtracting it on the other side, let's fill in what we can here. So 3.74 plus 1.96 times 0.36 over root 64. 0.36 over root 64, 1.96, and 3.74. So let's go to our interval now. 3.74 plus 1.96 times 0.36 over root 64 gives me an answer of 3.8282, and minus here 3.6518. Okay, so we've got a nice little range there of a confidence interval for the mean value. We're now asked to carry out a hypothesis test. So let's state our hypotheses first, always our first step, to see whether, or we're testing the newspaper's claim. So the newspaper's claim was that they have a different score. So we're going to test, and we're going to test our assumption, or base our assumption on whether the score has changed or not. We're going to say, first of all, that it has not changed, and we're going to test whether that's true or not, or whether that can be taken as true or can be rejected. So the null hypothesis is that there's no change, and I suppose to maybe let's tie that back better to the question here. So we'll say Galway's score is the same as the country, and the alternative is that it's not. So we're testing whether it is the same, and if it's not, then we can reject it and we're happy out. So we look at our confidence interval. 3.87 is outside the interval. So as 3.87 is outside the interval, we reject the null hypothesis. There is evidence to suggest Galway players have a different mean score. So we're basically saying here, because our test here was a test on the population mean 3.87. We tested it, we constructed that confidence interval based on our sample. We are 95% confident that the actual value is within that range there. 3.87 isn't within that range, so therefore we reject that claim that that is the population mean. So we have an idea here, or 95% confidence that the Galway mean is different to 3.87. And in fact here we might say is probably even lower, that they have a lower score than Ireland. A national newspaper conducts a survey on a random sample of N teenagers. 35% of the sample said that they play the online word game every day. Based on this, a 95% confidence interval for percentage of all teenagers who played the game was calculated. Corrected one decimal place. This was the interval. Use this to work out the value of N of the number of teenagers surveyed. Okay, so what we have here is a confidence interval for population proportion. So what I would say to do first of all is just remind yourself of what a confidence interval for population proportion looks like. Okay, and P1 minus P over N 1.96 minus P hat. So that's what a confidence interval looks like. If we compare the things that we have here, I could line up each of these in the following way. So I could say the value to the right, the 43.5%, that must match up with the yellow value here. Similarly, the green side there must also agree, because that's how the interval would have been constructed. If I go through the question, 35% of the sample said they played the game, that's P hat. Okay, so that's helpful to me in calculating my sum here. We also know that for this error, we'll be using P hat, even though it says P in the formula, we'll be using P hat anyway. So let's lay this out. P hat plus P hat 1 minus P hat over N should be equal to 0.435. Converting to a decimal there, because generally we're working in decimals here for these questions. So that should be equal to 35%. Let's keep going. So let's fill in these values. 0.35 plus the square root of 0.35, 1 minus 0.35, all over N, which is a sample of N teenagers, because that's what we're trying to calculate, is equal to 0.435. Okay. And I forgot my 1.96. Forgot my 1.96 here. Okay, that's important. Let's not forget that. So 0.35 here. Okay, 1 minus 0.35 all over N equals, and let's subtract the 0.35 there. I'm not going to trust myself anymore. Could have been a disaster. 0.085. Okay, again, we can also divide by the 1.96 as well. So 0.2275 over N equals 0.085 divided by 1.96, which gives me 0.043367. Okay, let's square both sides here. 0.2275 over N equals this last answer squared. So I'm going to try and keep that with me. Okay, so we get 289 over 153664. And then doing some little bit of work here to get, let me see, I'll take this up a bit higher so that I have a bit more space. Multiplying N up here to get 0.2275 divided by 289 over 153664 is going to give me an answer for N of 120.946. Because N is a sample, is a number of people, we have to go upwards, so we round upwards to 121 teenagers. So you can see there how we lined up the confidence interval with the appropriate numbers to make it work, and then we're solving for the unknown value of N there by removing everything around it. So very similar to some of the questions we've done, but maybe slightly different in the setup there for it. So just watching out for that sort of one. I'm going to skip over this question and kind of focus on the ones maybe here that I've highlighted that hopefully kind of point out some different parts for us to consider. So we're looking next at a company that produces eye drops. The amount of liquid in the bottles follows a normal distribution with a mean of 10 and a standard deviation of 0.8 milliliters. Find the percentage of bottles that contain less than 9.85 milliliters. Okay, so for me reading this question, I'm looking for the percentage or proportion of bottles that contain less than 9.85 milliliters of liquid. Essentially, I want the probability that if I pick a bottle, that it would have less than 9.85 milliliters of liquid here. Okay, it's not a sample. Okay, it's not a sample that I'm looking at. It's just not a sample. It's kind of That's kind of it, I suppose. So let's fill this in. So I'm going to use a z-score here. So my z-score is x minus mu over sigma. So 9.85 minus 10 over sigma, which is 0.18. So let's try that. 9.85 minus 10 over 0.18, which is minus 0.833. So we'll do 0.83. Okay, minus 0.83. So we are looking for the probability that someone is, let's try and get a bit more accurate, so we're around about here, minus 0.83. We are looking for the probability that somebody is in this region here, to the left of that. So that's kind of where we're looking for them to be. So that's the probability that they are less than minus 0.83. That's going to match up with the probability of them being greater than positive 0.83. So that would be this region here. Okay, so let's match up some of these. So those two regions there, they should be identical. I've drawn them quite poorly here, but they should be identical because of the symmetry of the curve here. So there we go, that's a bit better there. So those two should match up. And again, then we should know from our work already that that's the same as the probability of z being 1 minus the probability of z being less than 0.83. We go to our formula and tables book, we go to the standard score table, we look for 0.83, which is 0.7967. So we're looking for 1 minus 0.7967. And I get an answer of 0.2033. Okay, so that's approximately 20% of bottles I would expect to have less than that amount of liquid in them. We're told now it is known that 55% of the bottles contain between 9.85 milliliters and k milliliters, where k is a real number and greater than 9.85, find the value of k. So we're basically looking at here. Okay, I know that the average value is 10, so 9.85 is going to be less than. So I basically have two values here, and I know that between those two values, 55% of information is included. So there's 55% of information included, which of course is 0.55. Okay, so we're basically saying the probability that the z-score value that I'm looking for is between the two z-score values that are relevant here is going to be 0.55. Okay, so let's try and lay this out in a way that's going to make sense to us without giving anything away. So the probability, we're looking for the probability that x is between 9.85 and k, which we could line up or match up with the probability of z being between, we already know for the 9.85 because that's coming from the last one, minus 0.83 and zk. Okay, and our zk value, we don't know what that is because we don't know what the z value is that corresponds with k there, but we know the minus 0.83. Okay, so this is going to line up in terms of creating this. I want to look at less than zk minus less than minus 0.83. Okay, I already know that answer from the previous section. Okay, that should all be equal to 0.55. So the probability that z is less than zk minus the answer from the last one, which was 0.2033. So 0.55 minus 0.2033 is 0.3467. Okay, so let's go back for that one. So the probability, or excuse me, I took it away, but I should have added 0.55 plus 0.2033, 0.7533. Makes a bit more sense there. Okay, so we're basically saying the probability that z is less than this other z value I'm looking for is 0.7533. So let's go look at it. We're doing a lot of work here really with just z scores. We actually haven't really gotten to our actual kind of values here. So 7533, we'll pick something that's kind of as close as possible to that really. So looking at my values here, 7533, I'm maybe thinking this value here, okay, is kind of closest, so 0.68. Okay, seems like a good bet for us here. So we could say that ZK is 0.68. Okay, so ZK is 0.68. Then using my Z score, 0.68 is equal to x minus 10 over 0.18, which means that x is equal to 10.12 milliliters. Okay, let's continue onwards. The machine used by the company to fill the bottles is serviced and adjusted. This is where our hypothesis is finally coming in. The company want to check if the mean amount of liquid in the bottles is still 10 milliliters. They take a random sample of 50 bottles. Let's highlight anything important. So is it still 10? 50 bottles, mean is 9.96. We're working with means here, so we have the different methods available to us. We might try a test statistic this time. So the null hypothesis is that the mean has not changed, that it's still 10. The alternative is that it has changed and it's no longer 10. The sample mean is 9.96. The sample size is 50. The standard deviations is still the same, I assume, because we're not told otherwise. So we'll stick with 0.18 for that one. So let's focus on the test statistic then. So the test statistic is x bar minus mu over sigma over root n. So 9.96 minus 10 over 0.18 over 50. Remember, we're kind of testing nearly how realistic is this answer based on the null hypothesis. So we're okay with using the null hypothesis in our calculation here. So I'm getting an answer of minus 1.57. Okay, if I consider my kind of regions here, I know that the critical regions are minus 1.96 and plus 1.96. This value of minus 1.57 is about here. It falls within that kind of fail to reject region, so therefore we fail to reject. We fail to reject as the absolute value of minus 1.57, which of course is just 1.57, is less than 1.96. So we fail to reject. So we would say there is insufficient evidence so at the 5% level of significance. So we fail to reject at the 5% level of significance. There is insufficient evidence to suggest the mean has changed. Okay, so basically in terms of this question, the machine is serviced and adjusted. They want to check if the mean is still the same. So we reject the null hypothesis. We say the mean is still the same. So there's insufficient evidence to suggest it has changed. It probably still is 10 milliliters. Okay, and I suppose there can be this perception maybe for us there in rejecting it, that's like a negative thing. But in fact here, that probably is the goal. Okay, the ideal scenario here is that they've serviced and adjusted the machine and therefore the mean has remained the same, because that's probably the average amount that they do want in the bottles. Okay, let me see. Have we another question or two to look at here? Two more questions. Okay, bear with me. So let's look at them. So 2015 supplementary question. Okay, the principal of a large school claims the average distance from a student's home to school is 3.5 kilometers. Okay, I see it claimed straight away, so I'm going to go with that, and also I'm noting that it's average. In order to test this claim, a sample of 60 students, so that's my sample size. They were asked how far they lived. The mean distance is 3.7 with a standard deviation of 0.5. Test the principal's claim. Well, let's just start by making our hypotheses. First of all, the null hypothesis is going to be the claim that the average distance is 3.5. The alternative is that it's not 3.5. Okay, straightforward enough. Let's lay out everything else we know. We know what sample mean is here, which is 3.7, standard deviation 0.5, sample size is 60. Okay, I'm going to go with a z-test again here. It probably is the most straightforward of the tests for mean particularly. So my z-test is x bar minus mu over sigma over root n. Let's fill in the values. 3.7 minus 3.5, because that's kind of what we're testing here. 0.5 over root 60. Running away on me. 3.7 minus 3.5 over 0.5 over root 60 is 3.09, which is going to round to about 3.10. So we'll stick with kind of an even 3.1 there. So looking at my test statistic then, we have said with a test statistic we are willing to accept anything within the range of plus or minus 1.96. 3 is going to be like here, so it's firmly in the rejection region or the critical region there. So we would reject the null hypothesis as the test statistic. So we'll say the absolute value of the test statistic, which is 3.1, is greater than 1.96. We could also say z-test falls in the critical region. Okay, thinking about interpreting there, we're basically saying this value is too out of the ordinary for us to ignore. Okay, it's too irregular for us to actually ignore here. So based on the test, based on the hypothesis test, okay, I'm writing the same thing all the time here because it's just kind of the easiest way to do it is to ensure I hit all the points, is nearly just kind of always kind of vaguely aim for the same things, but you're more making sure you include the correct points here. So mention of the level of significance, mention of why you're rejecting it, and tying it back to the context of the question. So based on the hypothesis test at the 5% level of significance, we reject null hypothesis. There is sufficient evidence to reject the principal's claim. So we could say there's evidence to say the claim is incorrect. The overall idea here is that what the principal has claimed doesn't line up with the information that we have, so therefore we're rejecting the principal's claim there. Okay. So continuing onwards, in the above sample of 60 students, 20% of them lived within 2.5 kilometres of the school. Find the 95% confidence interval for the proportion of students from the school who live within 2.5 kilometres. So let's lay this out. We're looking for proportion now. Sample proportion is 0.2. Again, sample size is still 60. Confidence interval for sample proportion, 1.96 times p hat. I'm just going to jump straight to p hat this time because, as we know, we've said it multiple times here, the formula is p, but we basically never know p, so we use p hat. So let's fill in anything that we can here. So 0.2 plus 1.96 times 0.2, 0.8, 60, 0.2, 0.8, 60, 1.96, and 0.2. Okay, and my confidence interval here is going to work out to be 0.301 and 0.099. Okay, and that's all we were asked for, confidence interval. Okay, you could convert it to a percentage if you really wanted to, but perfectly content there because we weren't directed otherwise to leave it as decimals. Okay, perfectly content with that. Okay, so we're saying basically we're expecting about 9.9, so about 10 to 30% of people live within 2.5 kilometres based on that sample of 20%. Okay, so we've an error there of around about 10% of a margin of error we're allowing ourselves. So it's quite a large margin of error, but also lines up, I suppose, with the fact that it's quite a small sample relative to, you know, as samples go, 60 is kind of small. So we're not done yet. Data from 10 years ago shows that at that time, so 10 years ago, 26% of the population lived within the school. Based on your answer, is it possible to conclude the proportion of students living within 2.5 kilometres has changed since that time? So essentially they're asking us here to test the proportion being 0.26 to see whether it's changed. So we would say as 0.26. We'll look at the interval. Is it inside it or not? It is inside, falls inside the interval. We could not conclude that the proportion has changed. So because 0.26 falls within the interval there, there's nothing to say that it couldn't still be that. Okay, there's nothing to say that that couldn't still be the case. So we would fail to reject if we look at it as an actual hypothesis test here. But if we're just kind of taking it a bit more casually, which I think is nearly what this question's looking for here, yeah, we couldn't conclude that because we don't have enough information. Okay, a statistician wishes to estimate with 95% confidence the proportion of students who live within a certain distance. Okay, they're not giving us that distance. She wishes to be accurate to within 10 percentage points of the true proportion. What is the minimum sample size necessary for the statistician to carry out this analysis? Okay, so what we're looking for here is we're looking for the margin of error to be 10 percentage points. So margin of error for population proportion usually follows our standard error with the 1.96 here, and we would like that to be 0.1. Looking at what they said here, she said a certain distance, the proportion of students. She hasn't given us this proportion of students, so we actually just don't have enough information here to use this margin of error. Okay, we don't know the sample proportion, we just don't have enough information there to use this version. We don't know what proportion she's looking at. We don't know what the sample is going to be, which I suppose will affect the proportion. So we kind of don't know where to go from there. So instead, we'll use the margin of error approximation, because that's all we've got. So we basically want 1 over root n to be equal to 0.1. So that's 1 over n equals 1 over 100, which means n needs to be 100. So her minimum sample would be 100. Okay, and obviously she could go more than that. But within 10 percentage points of the true population, yeah, minimum sample of 100 is needed there. The within 10% means we can be plus or minus 10% is kind of what they're saying there, and that's why I'm just tying that immediately to the margin of error. Okay, so interesting point there, I suppose, for us to look at, that we just don't know enough information about P there to use that version. So instead we'll use the standard error there. Okay, now we see we've some more questions there. As I say, I'm just kind of picking and choosing some of these questions here that are kind of, there's overlap really across all of these questions anyway, but just picking a few that'll stand out, I suppose, that kind of offer different things. So looking at this question from the deferred paper for 2022, so over a season of shows that Mike's scoring some shows. There's kind of some context missing here from earlier parts. I think it's actually in the scatter plots and correlation section. But over the first season of shows, Mike's scores were approximately normally distributed, mean of 31.6, standard deviation of 3.2. Okay, all of this important. 12 acts were picked at random, and the scores given by Mike were recorded. Work out the probability that the mean of these 12 scores is between 30 and 32. Okay, so let's have a look at this one. So we'll kind of lay out this one a little bit. So this one, not immediately a hypothesis test, more really to do with a Z-score and a kind of Z-test question. But we're basically looking for the probability that a particular X value is between 30 and 32. So that's going to require us to even just work out the Z-score values for both of those. This here is a sample test question, so we just make sure that we include the correct formula for that, making sure that we're kind of even just considering it's to do with population, it's to do with sample means as opposed to just particular values. So 2.17 and 30 minus, oh sorry, that filled in the wrong value there for the mean. 31.6, yeah, that's a bit more. Looks a bit more like it, so 0.43. And change this to 30 is minus 1.73. So we are looking for the probability that Z is between minus 1.73 and 0.43. Okay, in terms of a little diagram maybe to help us here, there's basically two values, 1.73 here, 0.43 here, and we are looking between those two regions then. That's what we're looking for here. Okay, so to me that says I need everything below 0.43. So I'm looking for the probability that Z is less than 0.43 minus everything below minus 1.73. Okay, that's kind of what I'm looking for that one. Okay, and again, by drawing a little diagram for ourselves, we kind of remind ourselves that less than 1.73 or less than minus 1.73 is the same as greater than positive 1.73, which is 1 minus positive. And there's a lot of different kind of maneuvering that we do here. And as I said, a lot of it even you can kind of get used to and you get a bit more fluid with. But again, if that's kind of, this is all working with Z scores more than actually kind of your hypothesis tests here. So just to kind of keep us moving through this one, I'm going to just jump straight on a little bit here. So 0.6664, sorry, I forgot a 6. And the next one here is going to give me 1 minus 0.9582. So I get 0.6246. Okay, so the probability that the mean of these two scores is between 30 and 32 is about 62%. Okay, and that's based on his work there. His mean of 31.6 seems reasonable enough. It's a small enough value to consider. After the second season, a website claims that Mike's score in the second season have changed relative to the first season, and a sample of 20 scores, so 20 this time, from the second season has a mean of 33.5. Calculate the p-value. So p-value is 2 times the probability that Z is greater than the test statistic. So we need to work out the test statistic first, obviously. And we say absolute value of the test statistic. So let's work out my test statistic. So we're saying, we're basically testing here whether the mean has changed or not, okay, relative to the first season of shows. So we're taking the sample mean that we've taken, 33.5, we're testing whether it's changed. So I suppose if we wanted to give a null hypothesis here, my null hypothesis would of course be that it hasn't. My standard deviation here, again, we're assuming has stayed the same, so 3.2 over root 20 this time, because we've tested 20, we've taken 20 scores. So 33.5 minus 31.6 over 3.2 over root 20, which gives me 2.66. 2.66 as my Z score here. So the probability that Z is greater than 2.66, so considering what that would look like, 2.66 is going to be up here. I'm looking for above this, which we can kind of see from the diagram is 1 minus the probability that's less than 2.66. Looking for 2.66 here. C is this one, 0.9961. So 1 minus 0.9961 is 0.0039. So my p-value is 2 times 0.0039, which is 0.0078. Okay, so that's my p-value. Comment on what can be concluded from this p-value in a two-tailed hypothesis test at the 5% level of significance in relation to the website's claim. Give a reason for your answer. So, as 0.0078 is less than 0.05, we would reject the claim. We would reject the null hypothesis, which was the claim that Mike's scores we would reject the null hypothesis, and we'll put a little bracket or note for ourselves what that meant, that the mean had not changed. So as this p-value is less than 0.05, we would reject the null hypothesis, which was the claim that the mean had not changed, that we made, in fairness. So there is evidence to... Now, the website said his score has changed, so if we want to tie it back to the website, there is evidence to support the website's claim. That Mike's scores in the second season has changed. Okay. So based on what we looked at with p-values here, we're basically saying that we always allow for a 5% chance that a certain value could occur, or a 5% probability of a certain value occurring under the null hypothesis here. Okay, that's kind of the minimum that we're allowing. Anything below that is considered statistically significant. So we're basically saying here that under this null hypothesis, so under the assumption that we made that his score hadn't changed in the second season, that would lead to a probability of about, what's that, 0.78% that we would have gotten this sample mean. Okay, so that's extremely unlikely, and therefore means that the claim we've made is probably also false. Okay, because it's not kind of holding up here. So therefore it's more likely that his mean has in fact changed, which was the claim that the website made. So tying it back to the website claim, that's kind of what we could conclude there. Basically, we would probably be in agreement with the website's claim that it has changed because the p-value is less than 0.05. Okay, so loads of examples there of different exam questions for us to consider, and loads of different points for you to look at within that. We've said there all along, okay, and as I've said even in the previous one, the different types of tests that you can look at, and what you should be seeing even from those exam questions there is the importance of you being able to interpret the values as well, and even just seeing there across those questions that it's not all just testing. Okay, obviously testing is a big part of the questions, but they pull in different elements of your inferential statistics across the board there. So being familiar with your confidence intervals, being familiar with your Z tests, being familiar with your Z scores, whether it be for normal values or standardizing values, or whether it be for sample means in your sample Z test. So just being familiar with all of that, and kind of how that relates into those longer hypothesis test questions.